So we're still thinking about free energy in this section, and this time we're talking about free energy of formation. You can follow along in section 16.4 of OpenStax Chemistry. So our goal here is to calculate delta G from delta G of formation and then use that to predict the direction of the spontaneous change. This is one of our many ways that we're going to talk about to calculate delta G. And remember that calculating delta G is important because it can tell us which way the reaction is going to be spontaneous. So here we're using standard free energies of formation. And so formation in this context means making 1 mole of a compound from its elements in their standard states. So here's an example of a formation reaction where we have 1 mole of HBr being formed from, in this case, half a mole of diatomic H2 and half a mole of diatomic Br2 in their standard states. So that's a gas for hydrogen and a liquid for bromine. And so that means that the delta G of this reaction is going to be the delta G of formation. We can calculate the overall change of this reaction, or any reaction really. We can calculate the overall delta G using the sum of all of the standard delta G's of formation for the products minus the sum, that was a terrible sum, minus the sum of all of the delta G's of formation for the reactants. And so this should look kind of familiar, should look like using the standard enthalpy of formation to calculate delta H for a reaction that you did in Chem 131. Like delta H, the delta G of formation of an element is always 0 because you would be forming an element in its standard state. And so there's no free energy change here to make bromine from bromine. Now, you'll notice that I've been saying here a lot of something about standard, and you'll also maybe notice that we've had a little degree sign appear on our delta G. The delta G with the little degree sign means at standard conditions or under standard conditions. And so these standard conditions, we'll talk more about them later, but they're conventions that we agree on in order to make comparisons between values. So delta G's under standard conditions, that means the pure form of the substance. If it is a solution, that means it's a 1 molar solution. If it's a gas, that means 1 atmosphere of pressure of that gas. And then the temperature is usually 25 degrees C. I say usually because in some other disciplines, like in biochemistry, for example, they use a different standard temperature. But here, standard means 25 degrees C. Okay, so it turns out then that delta G equals delta H minus T delta S, and delta G equals the sum of the formation energy of the product minus the sum of the formation energy of the reactants. Those are saying the same thing. You can get the same answer either way you calculate. So here we can answer this question: is HBr thermodynamically stable with respect to its elements at 25 degrees C? Okay, in order to answer that question, we're finding delta G. Delta G will tell us whether it is spontaneous to form HBr or whether it is spontaneous for it to remain stable as elements. Okay, so we're looking for delta G for this reaction. So we could use delta G equals delta H minus T delta S, and we could calculate delta H for this reaction and delta S for this reaction using the using the enthalpies of formation and using the standard molar entropies. And you learned how to use standard molar entropy last week. So if you were to calculate delta G this way, then if you can find delta H, okay, that's going to be, for delta H, that's going to be product, so negative 36.3 kilojoules per mole, minus the reactants, so that'll be 1/2 of 0, plus 1/2 of 0. Okay, so that one will be negative 36.3 kilojoules per mole. Minus, we're going to use 298, so 25 degrees C for our temperature, times delta S. So to find delta S, we're going to use our standard molar entropies. So we'll do 198.6 joules per mole times Kelvin minus, so now we'll do our reactants, 1/2 of 130.6 joules per mole Kelvin plus 1/2 of 152.2 joules per mole times Kelvin. And if you do all that, I get that delta S for this reaction is 57.2 joules per mole times Kelvin. And I can make that into kilojoules by doing 57.2 times 10 to the minus 3 kilojoules per mole Kelvin. Okay, so I can put that in here so that way all of our units are in kilojoules. And so that'll be 57.2 times 10 to the minus 3 kilojoules per mole times Kelvin. All right, and so if I calculate that, I get that delta G equals negative 53.3 kilojoules per mole. All right, I can do the same thing using delta G of formation. So here I'm going to draw a line to divide my problem. With delta G of formation, we said we do products minus reactants once again. So we'll do that here. The products are negative 53.4 kilojoules per mole. And the reactants, so that'd be 1/2 of 0 plus 1/2 of 0. And so our delta G using delta G of formation is negative 53.4 kilojoules per mole. So at the level of significant figures that we have, we see, look, these are the same value. Alrighty, so you can do that. And, which of those is easier and which of them is better kind of depends on what kind of information you have. So here we see that using the delta G of formation is a lot easier because we have a formation reaction. That's not always true. Okay, so then to answer the question, if delta G is negative 53.3 kilojoules per mole, then is HBr thermodynamically stable with respect to its elements? Yes, we see that the reaction is spontaneous in the forward direction, so that means that HBr is more stable than the elements. If you have elements, they are going to spontaneously form HBr under standard conditions. Cool. So we can do that again. We can figure out whether a reaction is spontaneous. Here's another example, the reaction of acetylene to form benzene. And so in this one, this is not a formation reaction, but we can still calculate delta G. All right, and so we'll do, once again, the sum of the products minus the sum of the reactants. So here, delta G for the products, so that'll be benzene, so that'll be 209.9 kilojoules per mole, minus the reactants, 3 times 124.5 kilojoules per mole. And so I get negative 163.6 kilojoules for that delta G. So is that reaction spontaneous at 25 degrees C under standard conditions? Yes, it is. Okay, I think you're getting the hang of this now. So would it be possible to find a catalyst for this process? So remember that a catalyst increases the rate of the reaction. It helps us go to the end of the reaction, go to equilibrium faster. So if this reaction is spontaneously moving in the forward direction toward the products, and we found out that it was because delta G is negative, then yes, it would be possible to find a catalyst for this process, because we can't change the thermodynamics of a reaction with a catalyst, but we can make it go faster. Okay, and finally, is it possible to synthesize benzene, not from acetylene, but here from graphite and hydrogen at 25 degrees C and 1 atmosphere pressure? All right, so once again, is it possible? That means let's find delta G. And we can find this delta G using delta G's of formation. So our products are benzene, so we've got 209.9 kilojoules per mole. And then minus we've got graphite and hydrogen, so that's going to be 6 times 0, because graphite is an element, plus 3 times 0, because hydrogen, H2, is an element. And if you weren't sure about that, remember, you could look in Appendix G in your textbook. And if you did that, you will find that delta G is positive 209.9 kilojoules per mole. So it is not spontaneous. It is not possible to synthesize benzene from graphite and hydrogen under standard conditions the way that it was possible for us to synthesize acetylene. Okay, so do some more practice. I think you're getting the idea of how to calculate delta G from delta G of formation.